Hello and welcome to the keynote session to be given by Professor De Luca. I have the privilege today to introduce the speaker. Occasionally in life, things that make you happy professionally coincide with things that make you happy personally, and this is one of those events for me. I'm happy to introduce to you Professor De Luca, who is now a professor of robotics in the Department of Computer Control and Management Engineering at La Sapienza in Rome. I learned La Sapienza means the wisdom. So he'll be bringing the wisdom today. He's had a long and distinguished history of interacting with and doing things for and being a leader in the Robotics and Automation Society. He has a long CV, and I'll summarize some of what I think to be the highlights as an introduction. He has been the editor-in-chief of the Transactions on Robotics, presided over some of the glory years of that transactions, including the grand split between the Transactions on Robotics and Automation into two separate transactions. He ushered in the Transactions and Robotics. He's been the general chair of ICRA in 2007. He'll be the program co-chair for ICRA in 2016 next year in Stockholm. He is an IEEE fellow. He's won the Distinguished Service Award that our society gives a few years ago. That's all nice stuff, but of course what we care about, the reason that one comes to a plenary session, is because of his technical contributions and credentials. He's won the Humboldt Research Award in 2005. He's won Best Paper Awards at the conferences that you care about, including ICRA, IROS, and BioRobe. And this year, one of his papers for which he's a co-author is a finalist. And the paper that was a finalist for the Best Paper Award this year is related to the talk that he'll give today. His research interests include human-robot interaction, dynamic modeling and control of robots with flexible elements, visual servo, nonlinear control of manipulators and wheeled robots. That is much of it related to the project that he currently leads in the FP7 program called SAPHARI, Safe and Autonomous Physical Human-Aware Robot Interaction. He's the coordinator for that. Please join me to welcome Professor Alessandro De Luca.
Thank you, Seth, and welcome to this keynote. I'm very honored to be having been asked by the organizer to talk about the research that myself and my group and other colleagues in a European project are conducting since a few years. So Control of Architecture for Human-Robot Collaboration is a title which tries to cover the many aspects that we have been developed lately. So let's say the domain of interest is human-friendly robotics. So we want to move away from traditional robotics. This is that used to replace human with robots, to the situation where humans and robots will collaborate. And this is going to happen, and it's happening already now, both in the industrial setting, so we talk about co-workers, and in homes, or in other service robotics application, both professional and entertainment. So this is the context, and in particular, we are interested in the physical aspect of this human-robot interaction. Of course, the cognitive aspect is as important, maybe even more, but without the physical aspect, you will see that you don't go farther. So my background is in robot control, so I present here a few control problems which are safety related and which are important in human-robot interaction. In particular, the handling of contact, which may be harmful, so they become collision, and how do you detect collision, and how you isolate this collision, and what the robot should do in reaction to that. And possibly I will present some solution that do not require any external sensing. They just can be implemented based on the robot's own perceptive sensing. Of course, this is kind of the last event when a collision occurs, so you would like to have collision avoidance continuously, permanently, whatever the robot is doing, and this will allow the task to run despite the fact that the human entered the workspace. There is another situation which is relevant, namely when this collision becomes intentional contact because human and robot would like to collaborate. So instead of escaping possible contact, you have to look for, the robot should look for contact with the human, understanding which parts should go into contact and how you handle this interaction at the physical level. And possibly, since this contact may occur at any place along the structure of the robot, like in whole arm or manipulation, then you would like to rely not on specific sensor like tactile sensor or proximity sensor or force torque sensor, if possible. So in this respect, these basic problems correspond to 3 layers of control architecture that we have been developing over the last 3-4 years. The lowest layer is safety. Safety in the sense of physical contact, so detecting collision and reacting to collision. Of course, this includes also mechanical redesign of the robot, which should be compliant, possibly at the joints, maybe with soft coverage, lightweight links, and all this mechanical part. From the control point of view, you build upon this mechanical and electronic advancement to design a safe strategy. And this is the lowest layer of our architecture. Coexistence, we call coexistence the fact that the human and the robot are sharing their workspace. So, of course, this is the most interesting part right now, but you don't have to forget about safety, because a coexistence without safety makes no sense. So safety is always present. On top of that, like in a subsumption architecture, you have these coexistence capabilities that you have to guarantee. Finally, collaboration. So this is the highest level of this hierarchical control structure. You can collaborate in several ways. Of course, we are interested in the collaboration which is physical, not contactless. Of course, you can exchange information with the robot by voice, by gesture, and so on, but even pushing in selected places the robot to let him change operation or task. And again, collaboration is important, but collaboration should coexist with the fact that other parts of the robot do not collide with the human, except for the selected arm or a hand or whatever part of the human body. And if everything fails, the safety layer is also always there. So in this sense, I will present some solution for each of these layers and some examples through videos that shows how they coordinate and what they represent in terms of robot behavior. So suppose that we want to do collision handling. So we start with planning a motion to prevent, of course, this collision. Then we execute the motion and we use our feedback to control and avoid in real time online collision. But if something fails, if the human is too fast for the robot or some unexpected motion occurs, you may collide, and so you want to detect collision. And you have to distinguish if this is intentional or not. And in case, you have to react or replan the structure. So the following slide concerns this aspect. And for the collision event, we developed after a few years a pipeline which goes from detecting a collision, so saying yes or no, there is a collision or contact, isolating a collision, which means locating the link where the collision has occurred and possibly also the position of this contact point. Identification means reconstructing the joint torque, which is caused by this collision, and eventually also the Cartesian force in this contact. This terminology comes from the literature on fault diagnosis, so it's fault detection, isolation, identification, and in fact, our solution sees a collision like a fault occurring to our system. And then you can also classify which type of contact has been. It's accidental, intentional, if it's severe. Of course, this metrology of collision is very important. And finally, react to as fast as possible and in the most intelligent way. The simplest reaction you can think of is to stop the robot. And in fact, in modern lightweight robots like KUKA or ABB or even Baxter, This is the standard reaction, actually the only reaction. In fact, in order to react in a different way, so for instance, to avoid that the robot collides with you and stop against your body, you would like to be more comfortable with the robot going away. In order to do this, you have to know which part of the robot has collided. So you need to have also isolation and not just detection. For doing this task, we use monitoring signal. Mostly of them are physically motivated, like tracking the total energy or the momentum of the system. And of course, if you have additional context information, you may take the best decision to proceed after you have classified your type of contact. So this is a general architecture where we monitor collision, and we may generate different monitoring signal, for instance, a scalar signal sigma for detection, or a vector signal which has the same dimension of the joint space or the command space of your robot. If one of these signals goes above some threshold, then you recognize that a collision has occurred. And of course, you would like to do this without external sensing or contact information. Once you have recognized the collision, you want to react, so you deactivated whatever the robot was doing, and you try to find some safe reactive motion. Of course, the nice thing of this structure is that the monitor is always on. So while you're reacting to a first collision, you're ready to detect even a further collision, and so on and so on. So while we, in our analysis, we consider one collision at a time, in fact, we can handle multiple collisions and successive and so on. So this is an application of this. I promise that this is the only slide with some equation. Which is based on our method on vector residual, which applies both to rigid robots, where you don't have joint or sensors, or robots which have compliance, even variable compliance joints, in case if you have a joint or sensor, you may take advantage of it. And this was the solution that we implemented back in 2005 and 2006. On the DLR lightweight robot while I was in sabbatical at Oberpfaffenhofen near Munich. So this arm has multiple sensing, in particular has a position measurement at the motor side and at the link side, and these two variables are different because of the harmonic drive used. And it has also a jointer sensor. So with this redundant set of sensor, you can extract 2 out of the 3 information which are important. The dynamic model of this robot is like the rigid robot under reasonable assumption introduced by Spong many years ago. So the first 3 terms that you see on the first equation are just the inertia, Coriolis and centrifugal term, gravity term, whatever. And then on the right-hand side, you have the elastic joint transmitted from the harmonic drive, and possibly an additional torque, which is the joint torque resulting from a collision, which has this standard relation with the Jacobian transpose times F. Pay attention that F may be a generalized force, so force and moment, and you don't know it, and you don't know even the collision point, so you don't know the Jacobian. So all this expression is unknown. The only thing that you may know or may estimate is tau k if you don't have any further information. The second equation is the motor equation, but this will be irrelevant for our development now. Why? Because we are interested in having a signal which, in a sense, is sensitive only to tau k, so a signal which is always 0, but is activated as soon as tau k occurs. And this signal is a signal computed in this strange way. It's an easy derivation to check that this R vector evolves like a first-order linear system, decoupled in components. And so it's 0 when there's no tau k. It grows like a first-order system responding to a step input. And as soon as tau k goes to 0, it returns to 0. So it has a nice filter property and of stability property. So you can assume that if k is large enough, if ki, this gain is large enough, then the residual vector is approximately equal to the joint torque resulting from a collision. And this gives you the detection capabilities. When one of these components, or the norm of this vector, is larger than a threshold, then you detect collision. The isolation properties come from a more detailed analysis, which I have not the time to have, but essentially this vector has structural zeros beyond the link that has collided. So by looking at the evolution of this vector, those components which are 0 remain 0. Then you can say that the link I, in this case, has collided, and this gives the isolation properties. For instance, this is an experiment conducted on the lightweight robot where a collision at link 4 occurs. We were moving only 3 out of the 7 joints of this robot. And you can see that the robot stops here in this. This is the motion, this is position and velocity. There is some transient depending on the reaction that you have. And if you look at the evolution of the 7 residual, the red dashed line are the threshold which have been tuned according to the noise and uncertainty, residual uncertainty in the dynamics. You see that you have a detection, these blue lines on joint 2, nothing on joint 3, something on joint 4, and then 5, 6, and 7 are 0. So the largest index that has a non-zero signal detected qualifies the colliding link, in this case, a collision at link 4. So what you do then? You start to do reaction. And reaction means trying to bring away the robot from the collision area. I mean, the simplest reaction is just to stop, but we developed a portfolio actually of strategies for doing this reaction. And here you can see different ways. So R is the residual vector, and you can see in the first video here that we are generating a reference motion for the robot proportional to the residual. Remember that the residual goes to 0 when collision is over and as fast as an exponential. Here we have another scheme which is a reflex torque. So it's the reactive torque is again proportional to the residual. And you can have, once the robot has been stopped after the first collision, of course it remains in a floating state, and when you go against the robot and you push it at any point, then it flows in different ways, smoother or with more jerky motion like in the admittance mode that you can see on the left. So this is a whole set of possibility. In particular, you can also try to preserve the original task, for instance, using redundancy. So if you have a Cartesian task, let's say a 3-dimensional task, and you have a collision, you can accommodate the reaction torque to this collision in the null space of some dynamic matrix so that you try to preserve the execution of the Cartesian task. Or if you have given a trajectory separated in path and time, in the joint or in the Cartesian space, you can imagine that you keep the path, but you time scale your motion. For instance, here in in this video, okay, this on the left is the famous Samia Dadin self-test of the method, while here on the left, you can see that the robot is following a path. As soon as there's a contact, he slows down, stops, and even reverse motion. But if the impact is too large, then it goes into a reflex motion, so abandoning completely the task. So you can imagine several strategies. You have the bricks, and you can build upon these bricks reactive strategies. Okay, so what about the second level, coexistence? So we would like to avoid as much as possible collision in this context. Of course, you have to put sensor in your environment, on the robot, or in the fixed environment, and there are multiple choices that you can do. You can also formulate an optimization problem in order to minimize the obscured area to the sensor, depending on the probability of motion of the human around the robot. We use Kinect, like many people lately, and you can use Kinect in several ways. For instance, you can typically use point cloud library, so you bring your information directly in the Cartesian space if you want to reconstruct object. We don't want to reconstruct object, we want just to measure the distance between the robot and the human, both moving, okay? So we found that the best solution would, the most efficient solution is to work in the depth space. In the depth space, you have information that you can process in such a way that the computation of the distance of obstacle point, like this one or this one, from some point of interest, which is one of the control points that we choose on the robot, can be done in an efficient way based directly in the sensor space, and including the fact that this distance, for instance, is the closest distance not to the obstacle point, but to the covered shadow of this obstacle point. So you are conservative in a sense, but this is very easy to be computed in real time, and we can run things at 200 Hertz or something. So if you put together this idea, so you have this type of behavior with, this is Fabrizio Flacco, our now postdoc, with a lightweight robot moving, doing a task, I mean pre-planned task, but as soon as he gets closer to the robot escapes based on this computation of distances and on some local strategy, artificial potential, vortex field. You can implement whatever you wish once you have this minimum distance information. And of course, you can also have multiple objects, not only human. I mean, the robot is avoiding everything. And in case you start the collaboration phase, in this case, the collaboration starts, but the video no. Okay, no, it starts again. Sorry. Okay, just by a gesture, a hand waving, and then you implement our method for reconstructing the contact force. And at this level, the robot follows the hand that was waved, in the sense that this is the target, and you have an exchange of forces at the contact level, in this case only at the end effector level. And of course, you see here that only the designated hand should be reached, while all the rest should be avoided. And this is the coexistent condition. There's the final part of this short video is interesting because Fabrizio, while holding the end effector, is pushing it against his body. And of course, the more you get close to the rest of the body, the harder it is for him to move the robot, because coexistence is more important than collaboration. Okay? In case there would be a collision, the reactive part starts, so the lower level of the safety is involved. Now, how do you distinguish between a collision and collaboration? You can use the same method, so the residual, and have, let's say, two filters with two bandwidth, and you allocate to the filter with the largest bandwidth the presence of hard collision, which are associated to unintentional contacts. A lower bandwidth filter on the residual, and then with a logic, very simple logic built upon, can tell you that the collision is not as hard, it's a soft collision, and you can interpret this as the intention to collaborate. For instance, in this video, Emanuele Magrini, which is the author also of the paper which was selected for the finalist, is showing an example of a situation where you collide, and the robot will stop, and after a while will resume its operation. And in some cases where the two residual behaves in a different way, then you have a detection of soft collision. So again, this was a hard collision. Now the third one, and you can see how Emanuele is stopping the robot in the third case. Okay, now the robot is not stopping, is ready to collaborate, so he can push it around. Here there's an admittance mode control implemented, okay? So once you have done this, we can really estimate the contact force, and in order to do this, in general, we need to have an external sensor that localizes the contact point. We have anyway an external sensor for guaranteeing coexistence. We use one or two Kinect in our lab. By combining these two information, so the internal information coming from the residual and the external information coming from the Kinect, which allows you to compute which is the closest point of the human to the robot, you can localize the contact point, so you can localize the Jacobian associated to the contact, and then you set up a simple equation where you replace the actual joint torque with the residual, and you solve this with a least square approach, for instance, a pseudo-inverse, and you can extract the Cartesian force. So this is just to give you an idea of what happens. So we process the data, we remove the robot from the depth image. We have a CAD model of the surface of the robot, and so while monitoring, when the residual goes high, we just track the closest point on the surface of the robot and qualify this as the contact point. And from there, you can estimate the contact force in direction and intensity. Okay, I will skip this. This is just a validation of how, okay, sorry. So this is the behavior. This is a video from IEEE.RAS 2014. So again, you see the two dots, which are the hands being tracked, and Emanuele can touch the robot at any place with the right or with the left hand, and this arrow that you see is the estimation online of the contact force. By the way, you could do this also while the robot was moving, but then it's hard to show things. So the robot is being kept in a rest position and then reacts accordingly. So this is working, and in fact you can estimate also double contact as long as this occurs on two different links. And with this information, you can shape some robot reaction for collaboration, so not for escaping from this contact, because you have recognized that you want to have this contact. For instance, you want to do joint carrying of a load or holding a part in place, and this could happen at any point along the structure, so this is a kind of a form of whole arm force manipulation. And we have implemented different schemes. So with reference to, for those of you who have been working with a KUKA lightweight robot and with the fast research interface, the admittance control law can be implemented in the velocity or position mode, while impedance and force control laws needs the torque mode. And they have been implemented at the contact level. Once you recognize the contact, you can design an impedance controller or an explicit direct force controller at that contact point. So in this sense, it's a generalization of what we study in textbook, joint impedance or end effector impedance. You can realize a controller which realizes impedance at the contact point, whatever this contact point is. Same for the force. So this is, for instance, is an example, but I think I need to skip this. So this summarizes for the impedance case what we are doing. So this is a joint compliance scheme. So you have a contact force here, you have some compliance at the joints, and this is how you realize things. Of course, you can have a Cartesian compliance, you have a contact force at any point, and you have some reference position at the end effector level, and the robot reacts to these external forces without sensing force at all. But if you want to do impedance, in particular, you want to modify the apparent inertia at the joints, you need some joint torque sensor. And similarly, if you want to realize Cartesian impedance, then typically you need a force torque sensor. So if you want to modify the apparent inertia, whatever this apparent inertia is, you need to measure force or to have an estimate of force. In fact, this is what we do. At a generic point, we can modify the impedance, so we can assign a desired mass spring damper at this point and react to whatever contact force is there. And in order to do this, we need not to measure, but we use our estimate of this contact force to implement our controller. Here you can see two situations in parallel. So the first where we don't change the inertia, so in fact we don't need an estimate of the force for this. We just need this to locate where the contact occurs. In the right video, instead, we are modifying the inertia. We can modify, of course, the stiffness or the damping, but here we decided just to modify the mass, and you can see that the transient is different in the various directions. The last part, and I'm almost done, concern the force regulation. Now, when you want to control force, you need to measure force, of course. This is obvious. Since you don't have a measure of the force, you use the estimate as a proxy of this force. And here you can tell, there's a regulation here to 15 Newton. So you decide a direction for the desired force, and then you implement this kind of direct force controller. But what happens in this case? When you push in the direction where you have commanded some desired force, the robot moves back if you're pushing too hard, or comes against you if you're pushing too soft, okay? But if you're pushing in a direction, you're not pushing in the direction where you expect to react with 15 Newton, of course, he will drift away, okay? Because you have a problem of inconsistency of the task between the human and the robot. It's exactly the same story that happened in the old time with hybrid force-velocity control and end effector being involved in contact with the geometry of the environment. If you're trying to apply a force in a direction where the environment is not capable of providing a reaction force, then you will accelerate in that direction. And this is the same that happens here. So what is the solution? It's very simple. Instead of assigning arbitrarily a force in the Cartesian space, you assign just a value, so a scalar value, along the direction which is being identified. So you have an estimated direction of the force, and you have an estimated value, and you modify your control action so that this value goes to the desired set. In this case, again, 15 newtons, and you can see that Emanuele is pushing the robot in different direction, in different point, and more or less this video corresponds to this force going to regulation, then going to zero, then pushing again here, and then back going to zero, and so on and so on. No matter where you touch the robot and in which direction, you don't have this drift effect. So this is the good implementation of the basic idea. So, summarizing, I have presented some sample of multi-year work, I would say, on safe human-robot architecture. So, going from detection to isolation to reaction, I hope that I was able to convey the difference between detection and isolation, and that the fact that there are more reactions than just stopping the robot. Collision avoidance is another layer. We have shown the possibility of distinguishing between intentional contact and accidental or hard collision. And then the idea of estimating sensorless, I would say, in a generic sense, the contact force is useful because this can be applied to any point of the robot, and you can then close basic control schemes. Of course, you have to combine this in order to realize some collaboration. So this is another story. These are the tools that you have available in order to build up some more sophisticated global behavior. And I conclude by acknowledging the contribution of many people, in particular Fabrizio Flacco, Emanuele Magrini, Milad Gerevan, a master student of myself, who was able to implement a poor man version of all this idea on a conventional industrial robot without having any information of the dynamic model of the internal torque or whatever. So, but still it works reasonably. And then, of course, Sami Adedin and Alin Albusheffer, where I spent 1 year in 2005, and also the Artificial Intelligence Lab, where Fabrizio spent some months during his PhD with Thorsten Kröger and Usama Khatib. Thank you very much.
We have time for questions.
Question.
Alessandro, thank you for a very interesting, inspiring presentation about a very actual issue. I have a question about your slide 9. It's the calculation or estimation of the joint torques caused by collision. So my question is, how does this relate to or is different from the disturbance observer that is more widely used in the
This is, yeah, okay. So this formula, okay, let me. You're referring to this formula, okay. This is the disturbance observer, but it's the correct implementation of the disturbance observer because it doesn't need inversion of the inertia matrix, it doesn't need an estimate of the acceleration, is a first integral of motion. So you can reformulate this as a disturbance observer. Absolutely. But this idea is very useful because once you have understood what you're doing, I mean, you can have, for instance, for the joint elastic case, you can design such residual for the collision on the link side and another residual on the motor side that you can use to detect other unknown torque, for instance, the friction torque without any model, and we have used this to compensate friction. You cannot do this if the joint is rigid, because otherwise, in that case, you would have these two torques acting at the same level, okay? And same thing, we have implemented this for the variable stiffness case, and there are variants where, for instance, you don't need at all to know which is the current stiffness to have a detector for collision, and so on and so on. I mean, slight variation of the same concept. But this is a disturbance observer.
I'm going to ask you to ask Professor De Luca offline, because I see that it's time for me to adjourn this session. Let's thank again Professor De Luca.